Okay, it's 1 o'clock. I think we'll start. So this is the thesis defense for Jacob. As committee members, we have Dr. Manoranjan Maji, who's from aerospace, and Dr. Doug Allaire from mechanical engineering. A little bit about what Jacob's been doing. Jacob, I've actually known Jacob from his his undergrad days, and then he worked with me on a TTI project, which was really to build autonomous cones that could be deployed on freeways and that could be used for sensing any kind of, let's say, so the idea being that there are a lot of accidents that happen on freeways because there are drunk drivers who come and hit work zones, places where people are working and say fixing up freeways. And so the idea would be this autonomous cone would basically follow these work zone places. And then if somebody, if there is some person, he or she, if they're incapacitated, if they're drunk, they would go hit this autonomous cone instead of hitting these work zone places, right? And so while he was working on that, he was researching some accurate localization. And so we both looked at ultra-wideband technologies, and that is the basis of this thesis that he's talking about today. Yeah, I'll stop there and I'll let Jacob present his thesis. Okay, it's all you, Jacob.
All right, perfect. So like Shri said, my name is Jacob Hartzer. I'm a master's student in mechanical engineering under Shri in the Unmanned Systems Lab. And today I will be presenting my defense entitled Decentralized Collaborative Localization using Ultra-Wideband Ranging. So today I will be covering the motivation behind the research. I will introduce ultra-wideband technology and the idea of collaborative localization. I will go over the theory behind the models used in my simulations, as well as the decentralized collaborative localization algorithm. I will discuss the results, both simulated and experimental, and cover any conclusions that I have. So first, I would like to talk about why I performed this research. So the idea of autonomous vehicles is becoming increasingly prevalent in society today, and there are a number of companies working on various levels of autonomy for both professional and consumer vehicles. It's predicted that autonomous vehicles will take up large portions of vehicles sold, with fully autonomous systems eventually taking over the market. These systems generally use a large stack of sensors in order to operate autonomously, and these sensors can generally be divided up into perception and localization in their use. So the perceptive sensors include radar, LiDAR, cameras, and ultrasonic distance sensors, whereas the localization sensors are the IMU, which includes accelerometers, gyroscopes, and a magnetometer, wheel and steering odometry, which allows you to measure wheel speed and steering angles, and finally a global navigation satellite system. This is generally known as GPS within the United States, but there are also other systems from China, Russia, and Europe known as Baidu, GLONASS, and Galileo. And while these global navigation systems are very good, they are limited in certain environments. So an example of one of these limitations is in cities, large buildings have the ability to obstruct many of the GNSS satellites. And this causes something known as poor geometry for geometric dilution of precision. And because satellites for GPSs operate by actually measuring distances, when a lot of the satellites are collinear, it becomes very difficult to measure horizontal displacements. And so this really degrades the accuracy of GPS of autonomous vehicles within cities. Additionally, when vehicles move into underground or garage environments, it is very difficult to rely on GPS. So as they transition from GPS to GPS denied environments, the vehicles have to rely on dead reckoning. And this is not very ideal as it is subject to drift and can degrade the accuracy of localization. Lastly, there are also examples of vehicles that need to operate in entirely GPS denied environments, such as these autonomous forklifts that operate in warehouses. They still must be able to navigate and localize, but they do not have the ability to rely on GPS or any other GNSS system. So therefore, we need some kind of sensor that is capable of allowing these vehicles to position that is not subject to drift. So now I'd like to introduce ultra-wideband and the idea of collaborative localization. So some of you may have heard that the iPhone has announced that they're adding a U1 chip to the phone. What this is a ultra-wideband transceiver. And ultra-wideband was first regulated by the FCC in 2002, so it's a relatively old technology. It's defined by a large bandwidth, low power radio. And what's very unique about ultra-wideband is it uses pulses that occupy the entire ultra-wideband bandwidth. And so what that means is that it actually shares the spectrum with other types of signals. And so if we have like a narrowband signal that is defined at a specific frequency, or a spread spectrum that operates numerous frequencies, ultra-wideband can share the spectrum by actually being so low power that it is below the noise floor of either. So it doesn't actually interfere with existing signals. And another benefit of using this ultra-wideband is that if, for example, this frequency was blocked, the other frequencies are still able to penetrate. And so this means that ultra-wideband is relatively immune to multipath errors. So why is this useful? We expect that vehicles are going to be adding ultra-wideband technology so that, for example, your phone should be able to connect to the car to determine if the vehicle is close to the phone or if the phone is inside. And so this would allow people to interact with their car using their phone or possibly unlock it. And this relies on ranging technology with ultra-wideband. And another example of the use case is actually to solve the problem we discussed earlier, where forklifts could use this ultra-wideband ranging inside of a warehouse to actually localize. And this really solves the issue of not having a global positioning system available in any kind of GPS denied environment. So how does ultra-wideband ranging work exactly? So here we have two ultra-wideband transceivers, and the dashed arrows represent time moving forward. So the way that the signal works is a single transceiver will send a polling message to all other receivers, and then the receiver will wait a fixed time step and then respond. And by taking the total amount of time that this loop takes, it's possible to calculate an average time of flight between the two. And by using what we know about the speed of light, it's possible to calculate a distance between the two. So the reason why we want to include this is I'm sure many people have been stuck in traffic before, and there are increasingly many vehicles on the road. So the idea is if we can leverage the number of vehicles on the road to improve localization accuracy of individual vehicles. So this idea is generally known as collaborative localization, and collaborative localization can be divided into two main types of architectures. The first being centralized collaborative localization, and any kind of centralized algorithm has a single computational center. So in this case, all of the black dots represent a single node, which would be a vehicle, and then the red center represents a single computational source where all the signals and measurements are sent to a single place. And then a overall state estimate is calculated from all of those measurements and sent back out to all of the vehicles. This allows the estimate to be very accurate and optimal because you have access to every single measurement. The issues with this, though, is subject to single points of failure and requires infrastructure to be built in order to actually leverage the number of vehicles on the road. And because these are both big downsides as far as rolling out collaborative localization technology, we are actually leaning more towards a decentralized method. And what these methods are, where each node does its own computation, such that there are measurements between the nodes that are kept local to each, and information is shared at a minimum. This creates a system that is much more robust and is very scalable to new cities. And that's why we decided to focus on decentralized methods. Now I will discuss the theory behind the error models that I used in my simulations, as well as the algorithm behind decentralized collaborative localization. So in designing the models for the simulations, I wanted to model the sensor errors accurately and have it reflect experimental data. So specifically for GPS, typical errors include atmospheric effects, multipath errors, and receiver timing errors. Generally, the GPS error model can be simplified using something called a circular error probable number, or the CEP, which is a circular symmetric distribution. So the CEP is a single radius in which it is 50% likely to land inside and 50% likely to land outside of that radius. So what is shown on the right are the different error or probability bands for each CEP radius. And so you can see that it becomes less likely as you get further from the true value. So the CEP value can be transformed to a circularly symmetric Rayleigh distribution. The Rayleigh distribution, for example, is shown on the right with different sigma values, and the probability density function is shown near the bottom. So we can convert the CEP to the sigma value for the Rayleigh distribution because it's actually just the distance root mean squared. So it's about 85% of the CEP. And so to find the errors for the GPS, we just take random draws from every distribution using that distance root mean squared. And we actually find the angle by taking random draws from a uniform distribution from 0 to pi. In order to model the ultra-wideband, it would be very ideal if we could assume that they were normally distributed errors just based on the Kalman filter assumptions. And so we wanted to evaluate the ultra-wideband sensor. To do this, we created a experiment where we set the ultra-wideband modules at 10-meter increments from 10 to 100 meters and found the errors in the distance measurements. So what is shown on the right is a normal probability plot where if the plot was perfectly linear, it would indicate normality. But because we have these nonlinearities near the edges of the plot, I didn't want to immediately claim that it was normal. So it was ideal to use a more rigorous test of normalcy. To do this, I performed a Hartzer test, which is a statistics test that measures goodness of fit of a normal distribution. It does this by using both the skewness and kurtosis of the distribution, and then uses a chi-square test to do a probability. So because the probability was less than our alpha value of 0.05, it was possible to reject the null hypothesis that the errors did not come from a normal distribution. Therefore, it was possible to assume the errors are Gaussian normal and zero mean. And this therefore means that we can assume this in the Kalman filter equations. Moving on to the Kalman filter itself, I'm sure many people have heard about this, but I'll just briefly cover it. The Kalman filter is also known as a linear quadratic estimator, and it is useful in dynamic systems because it uses a two-step process using a prediction step and an update step, where the prediction generally uses the kinematic models of the system, and the update allows you to have measurements of the state using any kind of measurement model that is linear. They are commonly used for guidance and control problems, especially in the automotive and aerospace industries. And it is possible to incorporate nonlinear measurement and process models by linearizing those models. And this is known as an extended Kalman filter. And so that will be the basis for the collaborative localization. So pictured here are the equations for the extended Kalman filter. There is a prediction step and an update step. So the prediction step uses this nonlinear model to update the state estimate, and a linearization of that model is used to update the state covariance. Similarly, if we have a nonlinear measurement model, we can linearize that and then use that to calculate the measurement covariance, the Kalman gain, and then use those values to update the state and the state covariance. So to actually use the decentralized collaborative localization algorithm, it is a approximation of the extended Kalman filter. And the reason why it's an approximation is because each node does not have perfect information about the entire state. It was derived by Luft et al., and it is a recursive three-step process. So very similar to the Kalman filter, it has a prediction step and a private update step, where private updates are measurements that are only obtained by a single node, but it also includes a relative update, where these are measurements of between nodes. And what's very nice about this particular algorithm is the number of relative nodes can vary with time. And what that means is the number of cars in our case does not need to be known ahead of time. And so that means that the vehicles can move in and out of range of each other and not affect the algorithm overall, as this very closely simulates how traffic actually works in real life. It was very ideal to apply this algorithm. So the way that we actually apply the DCL algorithm is by creating a joint state. So what we do is all of the states that are within measurement range of the single node are combined to form this joint state. And similarly, all of the covariances are combined to form a joint state covariance. They are initialized using the best guess at the initial measurement time of each vehicle. And because the vehicles are uncorrelated as they initialize, we actually set the cross terms to 0. And what's very interesting about the DCL algorithm is that we are able to keep track of how the processes and private updates affect the cross-correlation terms. And the way that we do that is we actually create this decomposition of the cross term, where each one of these estimates is held by the separate vehicles that are then combined to form an overall estimate of the cross-correlation terms. And since we can decompose this in any way we want, to simplify it, we assign the original cross covariance to the first vehicle and an identity matrix to the second vehicle. So because the DCL algorithm is an approximation of the extended Kalman filter, you'll see that the equations are extremely similar. So for a control step, also known as the prediction equation is identical, and so is the covariance update term. Both of these equations are identical to what you see from the extended Kalman filter. The only difference is that we want to keep track of how the prediction affects our estimate for the cross-correlation term. And so that's why we multiply our linearized model times our last estimate. Similarly, the private update has almost identical equations from the extended Kalman filter, where once again, the only difference is that we again have this equation where we keep track of how the private updates affect the cross-correlation estimates. All of the remaining updates are the same. And mathematically, we should be updating the other vehicles' estimates as well, but we actually negate this because we want to minimize the amount of communication between the vehicles unless there is a relative measurement that takes place. So finally, the very interesting part of the DCL algorithm is when you have relative updates, and this is where it starts to get a little bit more complicated. So to do this, we actually have to finally share information between the vehicles where we combine the individual estimates of the cross-correlation terms for both vehicles in order to get this actual cross-correlation term. And then once we have that, we actually find a joint state estimate for the measurement covariance and the Kalman gain. And so what we're actually doing is, in most common filters, if you have a 6 degree of freedom system, this will be like a 1/6 matrix. But because we're actually doing a relative measurement, this then becomes a like 1/12 in our case, because we're taking into account both of the vehicles' state estimates. So we're finding the linearized model about both vehicles. So this allows us to update both the vehicles' states at the same time using the calculated Kalman gain. So we also have to update not only the covariance terms for the vehicles I and J that are being measured, but also all of the remaining terms for any other vehicle that is not measured. And so this is where we actually find our updated covariance terms for vehicles I and J. And then we, once again, will decompose the covariance terms. That way we can, once again, start to keep track of the process and private measurements. So this is where we take the actual term and assign it to the first car, and the identity matrix will be assigned to the second vehicle. And then all remaining vehicles are, the estimates are updated by, essentially this is a gain term, by determining the difference between the previous step and the current step, and then that is multiplied times all the remaining estimates. So that's the DCL algorithm as a whole. And so now I will start to talk about the results, both simulated and experimental. So I'm going to take a quick drink of water. So the DCL simulation that was created actually models a indeterminate number of vehicles and actually individually models the random sensor errors for each. So we have access to IMU, odometry, GPS, and ultra-wideband sensors at any given point in time. Additionally, the simulation handles the landmarks and the collaboration between the vehicles, as well as simulating the network between them. Each vehicle has a onboard simulated computer that has multiple estimation algorithms running simultaneously. So it has both the extended Kalman filter and an extended Kalman filter with ultra-wideband landmark ranging. And it also has the DCL algorithm with vehicle-to-vehicle ranging. Overall, it was programmed in MATLAB to increase development speed, and it was included with Monte Carlo simulation capability. So the Monte Carlo simulations allowed us to run 10,000 runs at a time of various different scenarios. It was parallelized to increase the processing speed, and it was run with and without landmarks and with and without collaboration between the vehicles. At the end of each run, the RMS position error was calculated, and then all of those runs were aggregated to a single matrix of values. So the first experiment that was run was two vehicles moving in parallel, and you can see that we have landmarks available to the side, and both vehicles would be moving in a straight line parallel to each other. We see that when the collaboration was added initially, we saw improvements, and with the addition of landmarks and the collaboration, we saw even greater improvements to the localization accuracy of the vehicles. Another experiment that was run was where we have four vehicles at a street crossing environment and landmarks on the corners of the street. Because the simulation was shorter, it was only run for 10 seconds, we saw a only minor improvement in the localization accuracy when adding collaboration. But because of the very good geometry, where we have very good sensing geometry from the landmarks, we saw much better improvements when adding the landmarks to the simulation. Finally, we tested a tunnel environment where essentially we had multiple vehicles moving all in parallel, but without access to GPS data. And so this was kind of our ideal use case for proving the benefits of ultra-wideband, both collaborative ranging and still landmarks. And so we saw that without GPS, we still only see minor improvements when adding collaboration. And so that's what this is here. We see a very slight improvement in decreasing the localization errors. And the reason why we believe that we only saw minor improvements is because even with collaboration, the entire system is still subject to drift. It is just less likely because you have 6 times as many sensor measurements, and so it's slightly less likely to drift. When we added the landmarks, however, it was actually very difficult to see, but this single line right here is the entire distribution. And so we saw a significant improvements in localization accuracy when adding the landmark. So that's actually about 100 times improvement in accuracy. And so we saw very substantial improvements when adding these landmarks. So to summarize the results of the simulation, we saw that ultra-wideband offers improvements with collaboration, and the larger number of vehicles, more vehicles led to increased accuracy. We even saw better improvements when adding landmarks, and the largest impact was seen in GPS denied environments. And this table just summarizes the numerical results that we're seeing. So some of you may have seen these carts before. These are the autonomous trolleys that we have in the Unmanned Systems Lab in Bryan. These were used in actually creating experiments for the algorithms to set up the experimental architecture. The robot operating system, or ROS, was used. This is a middleware that manages data streams between sensors and computational nodes. Sensor measurements can be published to ROS topics, and algorithms can then subscribe to these topics to receive data. What's also very useful about ROS is that you can record and then play back these data streams. And so even if something is not running in real time immediately, it is possible to rerun simulations with actual experimental data to see how algorithms would perform. And this allowed for much more rapid algorithm development and debugging. So in order to use ROS, the Decawave EVK 1000 modules, which were the ultra-wideband sensors we used, required a new ROS driver. So I wrote this in Python 3 using PySerial. And what this allowed is for all of the distance measurements to be published to ROS. And what it does is it actually creates lists of all of the different sensor measurements, because each ultra-wideband module can sense multiple at the same time. And so it publishes all of that information and makes it available to the DCL algorithm. The experiment as set up used the autonomous trolley that I mentioned earlier. The trolley has access to a number of sensors, the same ones that were simulated, in fact. So it has access to IMU, wheel odometry, GPS with the addition of RTK corrections, and ultra-wideband ranging to both collaborative and landmark ranging. A quick note about the GPS is that we also had RTK corrections available, and this was used as the ground truth, as RTK GPS allows us to have accuracies as low as 2 centimeters. Additionally, the golf carts were tested with different localization algorithms, the same as previous, where we have the extended Kalman filter, the EKF with landmark ranging, and the DCL algorithm with vehicle-to-vehicle ranging. So I would like to show, so here's an example of some of the data that was collected where the green line represents the DCL state estimate, and the red line represents the RTK GPS. And so this was just crossing the street without any landmarks, but with a simulated vehicle on the street corner. And other experiments include just driving down the street in a straight line. And this one, for example, was done without access to GPS in order to more closely approximate driving in a tunnel or any other kind of GPS denied environment. So overall, all of the experiments were aggregated. The results showed very similar things as the simulations, where ultra-wideband did offer improvements with collaboration, and we saw even greater improvements when using landmark ranging. The largest impacts were seen in these GPS-denied environments, and a summary of all of the actual numerical results are shown in this table. In the future, we would like to expand the simulation to have GPU arrays to possibly increase the computational speed. Additionally, we would like to increase the number of ultra-wideband tags used. Currently, we only have 4, but the current system can manage up to 12. Additionally, we'd like to use multiple moving vehicles. This wasn't possible due to limitation on testing with the pandemic. So we'd like to be able to validate with the time varying state estimates and also test the state exchange between vehicles. Finally, I would like to do more tuning with larger sample sets because each vehicle's run was limited to about 30 to 40 seconds. We don't have a lot of data, and so it would be nice to be able to have much larger data sets to to have a better EKF tuning. So in conclusion, the thesis work produced a number of contributions. There is now a flexible collaborative simulation that simulates various scenarios and vehicle parameters. It also has the ability to test Monte Carlo simulations. Additionally, I developed a Decawave-Ross driver package that is now available to the public, so others can also utilize these Decawave modules. I created a validation for the ultra-wideband error model, so that way it is valid to assume that the errors were normally distributed. And finally, I have at least a approximate validation of the DCL algorithm that was developed by Left. So in conclusion, ultra-wideband ranging offers localization improvements. This is seen both in the EKF and the DCL algorithms. We see that landmarks offer larger improvements, which is very promising for GPS-denied environments, such as garages or warehouses. The decentralized collaborative localization algorithm showed consistent and stable localization improvements, and we saw that in the simulation, greater numbers of vehicles led to larger improvements in localization accuracy. I would like to share my references for the slides. These were the text references, and these were the image references. And at this time, I would like to open the floor to any questions.